to deliver his talk.
Thank you. Okay. First, I would like to thank Professor Yao's invitation. And then today I'm going to present some overview of our recent series of our recent works in this area. And then my title is called Small but Mighty. The Chinese translation could be 小而精. Okay, yeah. So we know there are three driving forces of the modern artificial intelligence. That is data, model, and computational power. Okay, so these three have been majorly driven forces for the development of modern AI. So essentially, data provide material, and the models and algorithms provide a mechanism to process these material. And but all of these processing process is really rely on the computing power. Okay, so it has been predicted. It's predicted that in the next 4 years, that all the human stock of the data will be used up for training the large language model. Okay, in the current speed. Okay, so by that is roughly by 2028. Okay, all the human data will be used up. So it's really not really sustainable for the current development of large language model. And then here I show a little bit outdated model, but it still illustrates the basic idea. Essentially, starting from 2008, starting from the first generation of large language model, this model size has been getting bigger and bigger. Okay, and the current, I think, large language model already reached the 400 billion parameter size. So it's really getting bigger and bigger. Okay, and even for open source, this large language model, if you want to deploy it in your local environment, so it could be quite challenging. For example, if we want to deploy the Meta's Llama 3, the 70 billion version, okay, so you need to at least have 140 gigabytes of disk space and also 160 gigabytes of GPU memory. And if because in that version it's using floating point of 16. Okay, so this requirement, this hardware requirement could be very challenging for a lot of users. Okay, and another very important issue is training this large language model will generate a lot of carbon dioxide. Okay, according to a study in 2019, training a small large language model at that time, okay, in 2019, most of the large language model is in less than 100 million parameters. Okay, at that time, if you train this large language model for one time, it could generate more than 500,000 tons of carbon dioxide. That's equivalent to the 5-car carbon dioxide emission in a lifetime. So it's really daunting carbon emission. Okay, carbon dioxide emission. Okay, so to surmount the challenge of these issues, so a natural question arises: is that possible we can train a smaller model with less data, but still get a comparable performance to those large model trained with massive data? Okay, so this is the question. So there are to surmount this challenge, there are essentially two research themes. The first is data compression. Okay, essentially the idea is whether we can train the AI model using less data. The other research track is the model compression. That is whether we can get a similar performance using a smaller model instead of a large model. Okay, I will talk about both of these research themes in my talk today. Okay, the first is data compression. Okay, Obviously, there are many of data compression techniques. One of the techniques we have been using is so-called subsetting or subsampling. Okay, and in computer science, many people call it as a core set method. Essentially, the idea is to illustrate using this simple toy example. Okay, suppose we have data set look like this, and is that possible? We can get a sketch of this data set so that has a similar, very similar to the original data set. And then, as I said, in applied math, in computer science, people typically call this set as core set. But in order to measure how similar they are, so we need to have some measurement, and depend on which measurement you are using. So you could come up with different this core set method or different subsampling or subsetting method. Okay. So let's first take a look at a simple example. Okay, suppose we have two variables and they have follow a simple linear relationship. For example, y equals a plus b times x. Okay, and in statistics we always assume there are some measurement error. That is y equals a plus b times x plus epsilon. Epsilon is some measurement error or random noise. Okay, so essentially, I generate 2,000 data points from a simple linear regression model. The true model is this black line. Okay, I generate 2,000 data points. Okay, and if I use full data to fit a least square line, okay, it's this dashed black line. It's hard to visualize because it's almost identical to the two line I generated the data. Okay. But however, if I use a uniform subsampling, the so-called uniform subsampling is each data point get the same weight to be sampled. Okay, and then I sampled 10 data points. Okay, and then I got because it's a stochastic algorithm or random algorithm, so every run I will end up with a different subsample. Okay, for example, in one simple run, I end up with these 10 data points. I use the green star to indicate them, and then I use these 10 data points and then refit these 10 data points using these squares. I get this blue dashed line. Okay, you can see it's substantially deviate from the regression line I generate the data. Also, the least square line that I use full data to generate. Okay, so essentially this says if you use uniform subsampling, you may not get a good subsample. Okay, and then we ask a question: so why this uniform subsampling doesn't work? Because if we look at this simple toy example, we see most of these data, okay, concentrate in data cloud, okay, in here, okay. However, we find that there are some data points, especially the 3 data points in the corner and 2 data points in the upper corner. These are most influential, okay, to the data fitting process. Okay, so instead, okay, we may come up with a different, we may slightly revise our idea in the uniform sampling. Instead of giving uniform sampling probability to each data point, we give a biased sampling probability. That is, we give a higher sampling probability to those data points is most influential to our data fitting process or training process. Okay, and give less probability to those data that is less influential in our data fitting process. Okay, obviously, in this toy example, because in 2-dimensional, and then we can easily using eyeball to identify which data points are influential. But most of the time, we have multi-covariate, we have multiple features, and then in the data set, obviously, we cannot use eyeball to pick up those data sets. Okay, so anyway, so let's eventually I come up with one idea, and I will talk about it in a moment. Okay, So using this influential subsampling, or actually it's called leveraging subsampling. Okay, we come up with these red points. Okay, I use red cross to indicate them, and I fit these 10 data points also using least square, and I got this red line, and you can see this red line is very similar to the true regression line that I generated the data. Okay, so then the next question is how we can translate this intuition into some mathematical formulation so that we can have an algorithm that we can work on it. Okay, so one idea is how do we measure the influence? Okay, the basic idea is very simple. So we have the least square regression line. We call it y hat. This is our predicted value. And then we do a perturbation. Okay, we say that if this value of y perturb a little bit, how drastic change it will have impact on this least square regression line fitting process. Okay, so this perturbation idea eventually translates into here. Okay, we just take a partial derivative of this with respect to yi. Okay, and then in linear regression, this turns out we have a closed form expression. Okay, so in the linear regression, typically this least square line, this fitted least square line can be expressed as data. Okay, this covariate x times the beta hat, that is the least square estimate of the parameter. Okay, eventually it equals a so-called hat matrix times y. Okay, so in statistics, we made everything intuitive because this is called y hat. Y hat means you give y a hat. Okay, so we call the H matrix as the hat matrix. Okay, so eventually you can see these perturbation idea come up with these HII is diagonal elements of this so-called hat matrix. This hat matrix is essentially a projection matrix. Okay, X times X transpose times X inverse times X transpose. Okay, so based on this idea, we can have a very simple this so-called leveraging algorithm. Okay, essentially these leverage score HII, we normalize it and make it as a probability, and then using this probability, we can take a subsample from the full data, and then eventually we find out, okay, the resulting we call the beta leverage estimate. This beta leverage estimate will be will have a similar performance as beta hat, the full sample least squares. Okay, and then in our 2014 the Journal of Machine Learning research paper, we studied the bias and variance, and later on we also studied the asymptotic behavior of this subsampling. Okay, so this is our early work. However, in this work, it seems everything is ideal. Okay, so we have nice formula, nice theorem, and so on and so forth. But this world is tough, right? Okay, so in the reality, the data point could be in any manifold, okay, in any shape or whatever. So, and it may not have response. Okay, sometimes you collect the data set, you haven't decided, okay, what do we want to do? Okay, and so what do we want to do? Okay, so you may just say, I want to select some data points that similar to that can give me a sketch of the regional data sets. Okay, so what we did is the following. Okay, suppose here I show a toy example that these data points form two donuts shape. Okay, and then what we can do is first use the optimal transport. Okay, transport these irregular shape into some regular shape. Okay, and then once it's in the regular shape, for example, in the 0, 1 cube, okay, in this 0, 1 cube, we can use a lot of technique. And here, one particular technique we use is in the experimental design, so-called uniform sampling, okay, uniform design. And then using uniform design, we can get these very uniform subsample, and then we transform using optimal transform back to the original data set, and then what we find is the subsample we take can really reveal the original data set sample, okay? And then things become more and more complicated. For example, okay, we studying the streaming data. For example, these internet traffic data or many other the communication data among different IoT devices. Okay, in this scenario, data just keep on coming in. It never stops. Okay, and then your memory, computer memory always have a limit. So in certain time, okay, you will overwhelm your capacity of your local computer. Then obviously you have to use a certain subsampling method to take a chunk of data, okay, in order for the analysis, okay? So we developed this so-called subsampling idea. So essentially, we have this one, okay. Eventually, we cut a segment in this data stream, okay, and then using this data stream, okay, as a surrogate of this whole data stream, and then do the analysis. Our hope is that the result we obtained from this segment will be as similar as those getting from this infinite data stream, okay? And I will not go into details, but show you some work we did, okay, in the precision agriculture, 中文翻译叫精准农业, okay. Essentially, the idea is I lived in Georgia. Georgia used to be agriculture industry is a very fully developed industry, okay. For example, before the Civil War, okay, there are a lot of plantations, okay, a lot of cotton fields, okay. Even though right now cotton fields is not a major agricultural product in Georgia, right now we have blueberry and many other things, okay. So because of right now the global warming, okay, if you listen to the news in China, and I think in the past 30 days, in the past month, China already experienced at least 5 or 6 major drought or rainfall. Okay, so every day you almost heard some bad news somewhere in China. Okay, and obviously, if you ask for climate scientists, they will tell you this really because of the global warming and trigger a lot of disasters. Okay, but in any way, so right now America also invest a lot of money in this so-called precision agriculture. Precision agriculture, essentially, the idea is that whether we can rely on AI to monitor the growth of all kinds of agricultural products, and so that we can protect them. For example, sometimes because of drought, okay, these agricultural products already have some you already got some idea they will not grow good, okay. Then in that sense, can we take some measure in the early enough stage so that we can still protect our farmer from significant loss. Okay, so anyway, we collaborate with our colleague in the agriculture department. Okay, what we did is the following. So we have this tractor, okay, mounted with different sensors, okay, and then we just go through these cotton fields, okay, and then we collect the data. In one morning, we collect more than 100 terabytes of the data. Okay, so our worry is always how to store this so much data. Okay, because we also only have a very limited capacity of store this data. Okay, this show you, okay, just in one round, okay, we generate a very high resolution of this data cloud. Okay, we are not only generate this data cloud, we also collect their moisture, all kinds of other index of these agricultural products. Okay, so we use a lot of, in this process, we use a lot of subsampling for the analysis. Okay, so then now I want to talk about another challenging topic we have been working on. Okay, so a couple of years way back, I think before the pandemic, I was in a small symposium, and then a representative from the Ants Financial, okay, called Mayi Jinfu, okay, they one of their employee came here to talk about transaction network. Okay, essentially, the Ants Financial, they have these humongous transaction network. Okay, each identity, each node in this transaction network is someone have this financial behavior. Okay, and then this the line between these identity means that they have a transition happens. Okay, and then the thickness of this line indicates how many transactions happened between these two identities. Okay, and then this transaction network is really daunting. Okay, they have billions of identity, billions of nodes, and 100 billions of transactions happen. Okay, so it's a really daunting network. Okay, and then in that talk, they use GNN graph neural network to analyze this data, but once again, they down the way during the computation, they use a lot of matrix technique, essentially reduce this gigantic network into a smaller matrix computation. Okay, so that they can get this computation done. Okay, so then we ask a question that is, can we do the systematic study? Okay, to get a subnetwork from this large network, okay, and so that eventually the analyze the result will be as similar as the results we obtained from the large original network. Okay, so for here, okay, I want to talk about the three settings. Okay, depend on what computational capacity you have. Okay, we may have three settings for analyzing this so-called huge or large network. The first thing is this huge network is so huge. Okay, you cannot even access this network. Okay, because all kinds of issues, maybe privacy, maybe other issues. Okay, the second is a little bit is in the opposite of this hard question. Okay, the regional network, the first is the easy one. You can access this network, okay, and it's not large enough. Okay, the second the one is this network is not accessible. Okay, it's not accessible means okay, as I said, it could be due to privacy. Okay, all kinds of issues. Okay, and then today I want to talk about something in between, that this regional large network is not in these two extremes. Okay, it could be accessible, but it's only every time you can only access a very small network. Okay, okay. So this is our setting. Okay, so as I said, the first setting is very easy. You can access, if you can access all network, then you can do analysis. Maybe down the way, the only issue is it could be flow your memory, but you can still take other measures. Okay, the second setting is too difficult. Okay, and the third one is something between. Okay, so we will focus on the third one. Okay, and so what we want to do is the following. Okay, so the subnetwork we got. Okay, we want to have this so-called local to global property. That is important indices of the nodes or edge are local feature, but with certain global information. Okay, so that even though we can access this small network, we can still tell some global idea. Okay, the second one is we want to do the local computation. Okay, the local computation means when we do any computation, we do not need to trigger all the the original large network. Okay, so the subsampling measure do not need to compute the important index of the all nodes and all edges if we want to do this subsampling method. Okay, so obviously in the literature there are already a lot of methods to do this. Okay, the first method is a graph and matrix method. So the basic idea is you treat it as a graph and then you get this so-called adjacency matrix. Adjacency matrix indicate whether these two nodes have any connection or not. Okay, and then you calculate the degree matrix, and eventually these two matrices you can generate this so-called Laplacian matrix. Based on Laplacian matrix, you can use all kinds of numerical linear algebra to analyze this. You can get spectral clustering and so on and so forth. Okay, the bad idea of this thing is that this may be only applicable to these. If we have multiple networks, they have a correspondence. Okay, then you can use this. Okay, but if we have multiple networks, they do not have correspondence, then this could be challenging. Okay, and another thing is I like to use the calculus, but in here there is no calculus, just the numerical linear algebra. Okay, and the second thing is if we analyze really a large network, okay, we can, instead of really analyze this network by itself, we can analyze its limit. Okay, because this network you can by imposing certain limiting process, eventually it can be converged to certain surface. Okay, it's a 2D surface, and then this is a so-called graphene or graphics, and Professor Zong just talked about one method in graphene research. Okay, and this method is also has its limitation. Is that you need to impose this limiting process. If this assumption is being violated, the resulting graphene or graphics may not be relevant to the original network data you are analyzing. So eventually, after we do a lot of exploration, we end up still with the manifold approach. Essentially, the idea is we nested this this network to some manifold. Okay, and because the manifold has a lot of nice property. Okay, a lot of calculus can be used then. And then we analyze this manifold, okay, and then to get some idea, okay. So in this manifold, then we enter this so-called differential geometry or Riemann manifolds, okay, research field. In this field, the key research theme is the so-called curvature. Okay, curvature essentially measures how rough or how smooth of a curve is, right? In the 2D curve, it's very simple. Okay, if we can write the two-dimensional curve using index t, okay, we can take the second derivative of this curve with respect to t, depending on whether you want to have his sign or not. You may take an absolute value. Okay, in two-dimensional, it's very easy. Okay, define this so-called curvature. Okay, however, when it's generalized, and the good thing of this curvature is that it satisfies the two desired property of our original aim. Okay, so essentially saying these two curves are identical if and only if their curvature are the same at every point. Okay. Second of all, they have this local to global feature. That is, for simple closed curve, the integration of this curvature equals 2 pi. Okay, so this you can link this curvature and its integration. Okay, together. Okay. And however, the curvature in high dimensional become very challenging. How do you define a curvature in the high dimensional manifold? Okay, but I will not go into details, but eventually we end up with this so-called Ricci curvature. Okay, and this Ricci curvature is something being used by this. You see the 6th picture in outside of this lecture hall. Okay, and one of they use for this Riemann conjecture or whatever. Okay, originally defined as a mathematical tool to prove these mathematical curvature, mathematical conjecture. But they later on is find out that this Ricci curvature actually is also very powerful in modern machine learning or artificial intelligence. Okay, so essentially it's an average of this something so-called sectional curvature. Sectional curvature is defined very simple. In each point in this manifold surface, you have two arrows, and then you measure the third edge. Okay, if you try to draw something like a triangle. Okay, and then you compare with the Euclidean triangle. Okay, how large or how significant it is. Okay, anyway, the Ricci curvature is essentially the average of this so-called sectional curvature. Okay, it's measuring the degree to which the geometry determined by a given Riemann metric might different from that from ordinary Euclidean space. Okay, so and the Ricci curvature is only for this manifold, but we want to define something for our network. Okay, in one opinion, this network you can think of as discretized manifold. Okay, but anyway, so mathematician Olivier come up with this simplified formula to calculate this so-called Olivier-Ricci curvature. Okay, essentially it's defined by the following formula. Essentially, we have two vertices, U and V, okay, or two nodes in the network. Okay, and then the Ricci curvature between these two nodes can be defined as 1 minus the Wasserstein distance, and then you need to artificially define some so-called density, because Wasserstein distance essentially measure the two density. Okay, two density, and here there is no density, so they define some artificial density. Okay, to make it a density, and then versus these supposed to be Euclidean distance between these two nodes, but the Euclidean distance between two nodes in the network, once again, is hard to define. Then typically they just use the shortest path in the graph to denote this thing. Okay, so this is the so-called Olivier-Ricci curvature. Okay, so why they define the Olivier-Ricci curvature? What's the relationship between this Olivier-Ricci curvature and the Ricci curvature in the manifolds? Okay, there is a simple proof. Okay, essentially it's saying as this network gets denser and denser, it's more like a manifold, and then the Olivier-Ricci curvature eventually is converged to the Ricci curvature in the manifold. Okay, so this is the idea. So essentially you can think of Olivier-Ricci curvature is discretized version of Ricci curvature. Okay, so anyway, so these are mathematical ideas, so we want to use it in our in subsampling. So we generate this network. Okay, essentially it has two communities. Okay, there are 3 nodes here from one community. There are another many maybe 50 or 20 nodes from another community. Okay, and then so if we calculate the Olivier-Ricci curvature, okay, because it's between each node, okay, we calculate this edge, the Olivier-Ricci curvature, we find most of the in community, these edge tend to be positive. Okay, edge between the community tend to be negative. Okay, then we realize, okay, actually we can use this to roughly get a sketch of this network so that it can still keep the structure of at least the community structure of a regional network. Yes, please. Let me go back. So what kind of the alpha or something?
Yes.
Okay, I think they just use a half or something. Okay, for convenience. Okay, So I'm a statistician. I'm not a mathematician. Okay, I just whatever we try. I think we try out several things and find that this works. Yeah, more or less this whatever could review this structure. Okay. Yes. Okay. I think I look at the program tomorrow or the day after tomorrow. Some mathematician will talk about how to revise this. I use a very rough idea. Okay, so may not be the best choice. Okay, and for example, here I just use shortest path, and then a lot of mathematicians they use a more delicate formula to do this so-called Euclidean distance. But then how do you define the Euclidean distance in a network? It could be another interesting research area. Okay. So, and then we try another one, a similar thing, and then we have some two community plus some isolated nodes and give us a similar thing. All the edges within the community tend to be positive, and between the community tend to be negative, and if they are isolated nodes tend to be zero, okay, almost close to zero, okay. So something like that, okay. So based on this, we come up with a very, very simple algorithm. Okay, so essentially like a gradient descent. Okay, we calculate two edges, their Oliver Reese curvature, the difference, and then we starting in this algorithm, we starting somewhere in this huge network. That because as we said, we can only access a small portion of this large network. We starting somewhere, and then we go from to the other edge. Okay, so that give us this maximum. Okay, maximum is like a maximum. This is like a gradient descent. Okay, so and we did a lot of experiment. Here I just show you a quick experiment. Okay, so we have a small network. I think this network only have less than 100 nodes. This network has roughly 200 nodes. This network has more than nearly 500,000 nodes. Okay, so this is from PubMed. Okay, they have this network. This is a political books that is each in the Amazon. Okay, if this buyer okay buy both of these two books, and then we draw a line, and this is a political blogs. If one blogger site okay reference the other blogger, okay, we draw a line. Okay, this is roughly the data size. Okay, because they are getting bigger and bigger, our sampling proportion getting smaller and smaller. We sample 10% of the edge here, and 5% here, and 2% of here. Okay, our computational time is put it in these parentheses, and it's very short. Okay, very fast. Okay, and then what we did is after we take a subsample, and then we apply this so-called community detection algorithm to detect, okay, how many community we still have, and then we compare with the original using the full data set. Okay, still apply the community detection algorithm. Okay, we calculate their difference. Okay, and we can see our algorithm turns out to be very accurate compared to many other stochastic algorithms or other available algorithm. Okay, so the further details can be found in our, I think, in our iClear data of last year. Okay, so now I want to move on to the next topic. Okay, so we still have some time. Okay, so we talked about data compression, essentially through this subsampling or subsetting. Now let's move on to the model compression. Okay, model compression side is this is a large model, how we compress to the smaller model. Okay, so in this area, there are four kinds of research. Okay, four research themes. The first one is the so-called pruning. It's very easy to understand. We have large, very complex neural networks. Okay, by trimming about the nodes and the edges, we end up with smaller neural networks, and then we use this smaller neural network to do the for the as a model, okay, and train the final train the final artificial intelligence model, okay. The second method actually is related to our first method. Is the so-called quantization. Okay, quantization. Actually, this method we have been using. We call it fine to coerce method. Okay, the basic idea is also very simple. Okay, so suppose in the system you use 16 floating points. Okay, and then that has a very high precision, but it turns out, okay, you don't need to use that high precision estimate in your neural network, okay? For example, you can reduce it to the floating point of 8 floating point and so on and so forth. So essentially, you just do these roundup, okay, and then use a smaller, using smaller precision data, and then obviously will save you a lot of computation power. The third one is, well, what's going on? Something. Oh, okay. Okay, yeah. The third one is most of these neural network computation essentially is a matrix computation. Okay, instead of using the large matrix doing the computation, you can decompose these large matrix into multiplication of maybe 2 smaller matrix, and then you store a substantially smaller matrix, and then these will save you a lot of computational power. Okay, and now I would like to talk about I will talk about the first method and the fourth method. The fourth method is so-called distillation. Okay, and then I will talk about in a moment. Okay, so let's talk about our first method. Okay, the first method we have been working on this research for these compared to this so-called deep model. Okay, we have working on for the wide model. Okay, the wide model, especially for this so-called non-parametric model, and a lot of times if you assume this non-parametric model have this Gaussian noise, okay, it's also so-called Gaussian process. Okay, so essentially the idea, we have a response, we have a lot of features of covariance. Suppose there are D of them. Okay, we want to fit fit kind of regression, but it's not a linear regression. It's an unknown relationship. Okay, we want to recover this unknown relationship of this one. Okay, this is a so-called non-parametric modeling. Okay, and then in our research, we are not only interested in fitting these unknown function eta, we also want to do something so-called ANOVA decomposition. That is, we want to understand each feature, how they contribute to the final outcome of our of the results. Okay, so we can decompose this function, this non-parametric function, in this into this form. Okay, mathematically just using averaging operator by imposing certain set conditions. Okay, very simple to do, but turns out that this simple trick in statistics really can give us a lot of information. But anyway, in order to fit this non-parametric function, typically we're working in some special Hilbert space, so-called reproducing kernel Hilbert space. Okay, the basic idea is we measure our data, and then this is a model. Okay, measure their distance, and then we add some penalty. And this penalty could be some differential equation, and could be simple curvature, as we talked about in a few moments ago. Okay, and then this curvature eventually will end up, if we analyze the whole thing in this reproducing kernel Hilbert space, we find that the minimizer is has a certain analytical structure. Okay, and then it's essentially some inner product. Okay, with and with these tuning parameters theta. Okay, and then this so-called representer theorem eventually tells us the minimizer of these will end up with the solution like this. Okay, the first part we don't need to care. Okay, this theta k part. Okay, is a fixed point. Okay, typically this m is a very small order. Okay, it's a 3 or 4 or something, very small. But the second component of this analytical solution is huge. Okay, it essentially says that it's a linear combination of these so-called reproducing kernels. Okay, each kernel is anchored in some each data point. So if you have 1,000,000 data points, you have millions of kernels, and then you need to do the linear combination. Obviously, and then if you plug in doing all kind of calculation, this will end up with the n-cubic computation, because essentially this is a least square. Least square computation is np squared. Okay, and the p in here is n, so you end up with n-cube computation. Obviously, this is not ideal, and then instead we come up with some so-called basis selection procedure. The basic idea is whether we can use a smaller number of bases instead of using these full bases. Okay, still get the similar performance. Okay, and there are a lot of research has been conducted. Okay, even one of the research we come up is still something like this. Okay, so the data points. Okay, the data points look like this, very scattered. Okay. Oh, this is essentially the basis. Okay, we want to select. Okay, there are a lot of them, almost as dense as some manifold. Okay, and if we use a uniform subsampling, we take some basis. It's very noisy. There is no pattern at all. Cannot missing a lot of important area. Okay, and the ABS is not ideal, and eventually we come up with this SBS idea. Okay, once again using this uniform design in experimental design. Okay, and then we sample some bases really very uniform. Okay, and then we also find out. Okay, if we doing fitting this model using the selected basis function, okay, it's a much smaller order, and the computational cost is substantially reduced. Okay, so and then we continue to move on. Okay, and then the last topic I want to talk about is this so-called knowledge distillation. This is the most important idea in deep learning. Okay, so the essential idea is also very simple. Okay, we have a very large complex neural network model. Okay, can we train a smaller model? Okay, but at the same time can have the similar performance as this large model. Okay, and then the reason they call the knowledge distillation is this large model you can think of like a teacher. Okay, this smaller model like a student. Okay, this is a process. It's like a student learn knowledge from the teacher. Okay, and Jeff Hinton in 2015 paper, okay, he called this process as knowledge distillation. Right now, knowledge distillation is still the most popular method. Okay, in the current neural network. For example, the Meta released this every time Meta release this open source, the large language model, they always release two versions. One version is a large one, and the other one is a smaller one. And the smaller one actually trained using this knowledge distillation idea. Okay. So in order to present this method, let's talk about the deep neural network. Essentially, it's a nested network. Okay, each layer, okay, have this function like this, and then we have this so-called weight W and the bias parameter, weight matrix, bias parameter, and then all of them putting together, we call it as our theta. Okay, because these theta are unknown parameter, we need to train from the data. Okay, and then in the knowledge distillation, the loss function have two components. The first component is very simple. Okay, so essentially saying, okay, these student neural network, it has a prediction result, and then we measure the distance between this prediction result with respect to the label. Suppose if we suppose this is a classification problem, okay. For example, it's like we want to identify what kind of animal in these in these images, okay, and like if this is a and each data point has a label, okay, this is a prediction label and the true label. They measure their distance. At the same time, they have a second component that is we want to learn from the teacher, so that teacher has a prediction. Okay, I want the student prediction is as similar as the teacher prediction at the same time. Okay, so then we use a lambda to control these two sometimes could be conflicting predictions. Okay, so this is the idea. Okay, the loss function. And then we realize, okay, these can be reformulated into some Bayesian paradigm. Okay, the basic idea is the first component can be treated as a likelihood function, and the second component can be treated as a prior. Then, if we combine the likelihood with the prior, then we can come up with the posterior of the theta, and then we naturally come up with some uncertainty estimates. Okay, so so we formulated the problem like this, especially in the classification problem. Okay, why is the label of the data depend on the image? Okay, it maybe follow the multinomial distribution. Okay, and then this H is this student neural network. Okay, and then we impose the so-called Dirichlet prior. Okay, this Dirichlet prior has this 1 plus lambda times pi. Okay, P is the teacher's prediction. Okay, and then lambda is a certain weight. Okay, and 1 is essentially is a equal probability being imposed. Okay, so and then once we formulate the problem like this, then we can show the posterior is a proper posterior distribution. Okay, and then in here, obviously, this lambda has impact on our model. So there are two extremes: lambda equal to 0, then these become a symmetric Dirichlet distribution. If lambda goes to infinity, this will goes to a point estimate. Okay, so anyway, so based on this formulation, we can show that posterior mode of our so-called Bayesian knowledge distillation will be equivalent. Okay, is equivalent to the minimizer of original knowledge distillation. Okay, and then in order to because this data parameter in the neural network is high dimensional. Okay, so in order to do this posterior sampling, okay, we use some Langevin Monte Carlo. Essentially, the idea is like a gradient descent, but you need to add some Gaussian noise so that it can avoid some local optimal. Okay, so this is a similar idea to the generative model have been used in many generative AI. Okay, and then we come up with some prediction uncertainty, especially this is D-ones has been used in statistics a lot because this is a classification problem. We cannot directly define some so-called variance, but we can define something similar, so-called D-ones. D-ones is like a variance in the Gaussian process. Okay, but this is for the classification problem. Okay, and we can also construct a credible interval in because it's a Bayesian setting. Okay, and I'm not going to talk about details. And we try a lot of real data, starting from very simple one, MNIST, these handwriting digits, until the classification CFAR 100. Essentially, in here, there are 100 class of image need to classify. Okay, so And then we compared these solely with teacher model, original knowledge distillation model, integration knowledge distillation with there is a so-called Bayesian neural network. This is a very old-fashioned Bayesian method in the neural network. And also there are some perturbation idea. Okay, perturbation essentially you perturb this neural network by removing some nodes from the original. Obviously, your prediction will be different. And this is a so-called drop-out idea in neural network. Okay, and then this perturbation also generate some results will have difference. Okay, and then this variation can be used to measure the uncertainty. Okay, so and then we try different models. Okay, something very large. For example, this VIT Vision Transformer. This is a very powerful method using as a teacher model, and then we use mu x net as a smaller. This is a much smaller model as student model, and then using this as a student model for this Bayesian knowledge distillation. Okay, and we can see, okay, this really gave us a very interesting uncertainty quantification. Okay, here is a lower uncertainty, means we have very confidence our classification, and you can see in MNIST this digit really clearly being written. But here we also have some high uncertainty that it has low confidence, and you can see these digits really very blurred. Sometimes it's hard to recognize which digit they are working. And similar, this is for fashion, MNIST, and Cipher 10, so on and so forth. Okay, Cipher 10, Cipher 100. Okay, the low uncertainty one, you can clearly tell, okay, what the image is, and then for the high uncertainty ones, and then it's hard to recognize what these images are. Okay, and then once again, these showing more MNIST data. This is the low deviance one. Okay, clearly spell out the digits, but for those digits, they have high deviance, and then turns out to be hard to recognize. Okay, and so on and so forth. Okay, and I'm not going to talk about this. Okay, and then we want to make sure, okay, our uncertainty estimate really makes sense. That is, for the MNIST data, we gradually add some noise to making it more and more blur. Okay, and then we supposed to see our accuracy for the prediction should be dropped. Okay, at the same time, our deviance, which measure the uncertainty, should be increased. Okay, and what we find, only our BKD, Bayesian knowledge distillation, seems keep on increasing. All the other ones, after a certain point, they have some turning point, and then have some weird behavior. Okay, so this is uncertain quantification. And then because we also construct a credible interval, we want to assess, okay, what's the coverage rate? And then it turns out our Bayesian this knowledge distillation is keep as the sample size getting bigger and bigger, is converged. All the other is not does not translate into their nominal confidence. Okay, so and so that's pretty much for all my talk. So all our lab members getting into contribute substantially to this research, and Jia Zhang and Shu Sen and Yong Kai and Hui Min and Lu Yang and Hao Ran, and also this is a collaboration with Professor Wensheng Zhou. Okay, that's all for my talk. Thank you. Right on time.
Well, thank you, Professor Ma, for his wonderful presentation. Now, who has questions?
Okay.
Okay.
I was wondering more about your. I was wondering more about the research procedure on like the community, the sampling from the community using
curvature.
Using curvature, and if you're kind enough to show the slide.
Okay. Yeah.
Um,
So this is the procedure.
I was wondering more about the procedure. So you said that the curvature of a community tends to be positive, while the curvature of the connection between community tend to be negative. So the input data is so is your input data classified as community and their connections already? And if so, how are we going to implement like certain method to pre-classify community and the segment connecting communities? Or is that a type of structural pattern that you have discovered that we can use to determine the community and its connection?
Okay, very good question. So essentially, the question is, my understanding is whether this community is given in priority. Okay, no, before the procedure, no. Okay, what we did is the following: in the simulation or in the real data. Okay, we first for the whole data. Okay, for the full data, for the full network, we apply this community detection algorithm. Okay, to detect how many community it has. Okay, for example, 5 community. Okay, and then we use our procedure, take a subsample, take a subnetwork. Once again, we apply the same community detection algorithm. Okay, maybe come up with 4 of them. Okay, we take a difference. That is a kind of very rough idea tell us, okay, whether this subnetwork really makes sense or not. Okay.
Oh, so this is like a separate part from the community detection algorithm, and I was wondering as well, could that be applied that maybe in the future to determine how many communities and how many segments connecting the communities one neural network has?
Yes, obviously, because this is just, as I said, this is just validation saying, okay, the subnetwork we are taken could make some sense. Okay, everything is still exploration, it's very exploratory. Okay, even for this, after we try some example, we find out, oh, it has this kind of phenomenon within the network is tend to be negative, tend to be positive, between network tend to be negative, and so on and so forth. Then we come up with essentially the community detection is downstream task. Okay, we use downstream task kind of saying, okay, the upstream task seems to make a lot of sense, but there could be a very open research area. Okay, and your question really spell out the key point of this research. Okay, can we come up with some other index to show, okay, how these subnetwork really make sense or not? Okay, thank you for your question.
Thank you so much.
Okay. Thank you.
Well,
Okay.
thank you, Professor Ma, and we can take a break.